In the last video of differential geometry, we have covered something which is called a parameterization of a curve. As you can see that a curve is just a static shape until we parameterize it. So this is a kind of a motion which is going around. So we have covered that in details. Also, as you can see, this is a kind of a parabola where a small particle, this blue one, is moving from the negative to the positive axis, the circle moving around. So all these things are telling that introducing a parameter like time t, we turn the shape into a living path. So when you define a function, for example, gamma t equals to something, cos t, sin t, or whatever, you're actually making a point move along the shape. Now a point moves along the curve and we can study how fast it moves, which direction it takes, and various other things, that is the motion, etc. So this is where the real geometry begins to breathe. So parameterization is something that we have already covered in the previous video. We have also covered something like this, a static parabola, and then the particle starts moving. So as t moves from negative to positive values, you can see that the function traces the entire parabola. So this gives us the same parabola, but now as you can see, it is moving point based on a parameter t. So from here we can say that the motion opens up an entire whole world of new geometry. So we don't just ask where is the point, we ask how is it moving. We can track the direction, speed, and the rate of change of every moment. So parameterization let us treat the curve like a path. So the curve transforms from a frozen figure into a dynamic motion story. And it is the difference between seeing a single road and driving on it. The parameter actually shows us how to ride. Now once we see things that are in motion, so as you can see on the left hand side, these are just random curves, but what I'm trying to mean is that once motion begins to reveal more than just a path, then we ask this question: how far have we moved at any given distance, that is about our position and speed? How sharply we are turning, that leads to curvature of the path, and how fast we are turning, that uncovers of how rapidly the direction itself changes. Now to answer all these questions, we need to go in differential geometry, but before that we will dive into something very special which is called the astroid. Now this is a typical kind of a curve which we will see soon, and it is not only visually interesting, it gives us the perfect test ground to understand how motion brings geometry to life. So our direction, how sharply we are turning, how fast we are going, in which direction, all these things will be now answered. And previously we have covered parameterization, so we have already seen that the geometry is breathing in life, that is the direction and the movement. So we start our today's video in understanding what is called the astroid curve, and obviously first the visual comes in. And how does the astroid curve looks like? Well, I can tell you that each one of you have seen the astroid curve, all of you, but you really have not noticed it. Now if you have seen the logo of Gemini, which is the Google AI tool, you can see this star, right? This one I'm talking about, and this is exactly how the astroid curves looks like. Okay, so this is already you have seen, but now that I am telling you, this is called the astroid curve, and why we are studying that also will become clear soon. So this is an astroid curve, just like the Gemini logo, and this is basically the construction. I won't say it is a construction, but as you can see, the circle moves around, it creates the astroid curve, or it traces the path of astroid curve. This we will also look in that. So it is coming from the word astron, which means star, and oid in Latin means like or resembling. So taken together, it is called astroid, means it is a star-like curve. But remember that astroid is more than just a star-shaped curve. You can see each of its corners are sharp, which are called cusps. It holds a mathematical secret we will explore. And as we trace and move along it, we will see that how the speed vanishes. That is, the geometry reveals itself in the sharp edges. So the astroid looks like a star. with four symmetrical pointy, I would say, arm which are called cusps, and hence the name. And here we will now answer the question that out of all the different curves in differential geometry, when we are talking of motion, why are we studying asteroid curve? Is this something very special to it? And to answer this question, yes, it is not only similar, but it is simple to understand. So we begin with something familiar. We all know what it is. This is a circle. It is simple, smooth and symmetric, the perfect baseline to understand the motion of the curve. And now you will see that we step into something a little bit more geometrically rich, and this is called the asteroid curve. Now it still loops back, as you can see, itself to like a circle, but it shares a symmetry. So in the previous lesson, what we have done is that we have already seen that using t as a parameter, we can parameterize a circle and a parabola. But now we want a curve that is using the basic function, but it is also not non-trivial. So a circle is considered trivial. Why? Because its curvature is constant, its motion is smooth and predictable, and it has not sharp edges. But here what we mean by non-trivial is this. By non-trivial, we are trying to mean that it is obviously not simple, it is not linear, and it requires a deep understanding of the geometrical structure. And as you see, that circle is trivial, but asteroid is non-trivial. Why? Because it has cusps. The derivative becomes 0 at corners. It is not the graph which can be explained by a function y equal to f of x, and the geometry is much more complex and much more rich. So a non-trivial curve has a little bit of a complex behavior. So the asteroid actually gives you a shape that is geometrically rich. That means it is non-trivial, and aesthetically engaging. That means it is visually interesting. I mean to say, it just tells the deeper mathematical insights, such as how speed approaches 0, or how the tangents may or may not exist, and something like that. So the question is that what is the mathematical equation which will give rise to asteroid? So this, if you're talking of asteroid, x to the power 2/3 plus y to the power 2/3 equals to 1. That is basically a typical example of an asteroid. So this is a static equation. Remember, this is basically a static equation. It is an implicit equation. Whether a point lies on the asteroid, but it does not tell how a particle moves around. And in order to know that, we have to define something in a parametric form. So you can see that we are just cubing the cos and the sine, and we are getting this beautifully exotic asteroid curve. So this is the parametric form, and this t is something for every value of t, we get a point x of t and y of t on the curve. But what does it mean to cube the cosine and sine? So as you can see, that it acts normally like a variable as t increases 0 to 2 pi, and it traces out the curve. So when we are talking about cubing, I was just asking, what does it mean to cube cosine and sine? Right? So cube cosine and sine actually means this one. Each value of t gives a point x of t, y of t on the curve, and as t varies continuously, as we will see in the animation, from 0 to 2 pi, the 360 degrees, the point gamma t also moves smoothly along the asteroid curve. So as you can see, the cubing actually gives that xt and yt describe not just where the point is, but it traces how the curve slows near the cusps, faster in between, and so on. So here is again the asteroid curve, but I would like to show you the animation. So if this red dot animates, so you can see it is going counterclockwise, then it touches and goes on. Again it goes counterclockwise and touches and go on. So this goes on, and this is where the asteroid curve is actually coming to shape. So a red dot, as you can see on the left hand side of your screen, traces the curve, sweeping it smoothly and gracefully in a counterclockwise motion. At the beginning, as you can see, the point starts at 1 0, then it passes through the four cusps, to the top left 0 1, left 1 0, bottom, and then back to the right. We will see the quadrants very soon. So as you can understand, the plot is very symmetric. Both axes and the aspect ratio is set to 1, and the asteroid looks geometric. So if I take a counter, say for example t, which I was taking the time parameter, etc. So as the t rises from 1 second, so the time passes on, the red dot moves along the smooth curve. And what is C? This cubing we have already seen. This actually gives rise to the symmetric shape. So the parameter controls the motion and the shape comes to life by one point by point. So the animation is in loop, so it will carry on. So as the t is increasing, the red dot is moving and the cosines are actually giving rise to this beautiful symmetric shape, and this is how it actually goes on. Now as we turn the page, now here you can see these are actually the values. So let me highlight this one. As you can see right in the top, 0, 1, this is the value of 0, 1, which it gives you the cos cube 0 and sine cube 0. Here the maximum value of t is reached, and this is t equals to pi by 2. Again 0, 1 have reached, this is where the curve reaches its highest point here. Again we reach minus 1 and 0. You can see this mathematical calculation, sine cube pi equals to 0 and minus 1 cube equals to minus 1, and this is another cusp which has got a sharp turn on the left. Now why I'm mentioning this cusp, this will come to use very soon when we will be talking of the velocity and the motion of the particle. Again 0 and 1, this is where it comes in, and you can see this is again another cusp which is downward towards this star. Now here is something which you might have noticed very interesting. I have mentioned the bottommost cusp as 0 minus 1, but the value is 0 minus 3 pi by 2. Now why it is so? Now in order to understand that, first we will see that what are the motion between the cusps. First let us understand the motion. So the quadrant is number 1 from right to top, right? So we are going from here to here. Right? Again, I will show you from this part to this part. This is the quadrant 1, so I have mentioned it as Q1. So the cusps here are a sharp point where the speed becomes 0. Then we move to quadrant 2, and it takes the shape from here and then down to here, right? From t pi by 2, and then the cusp comes over here. Then we come to quadrant 3. This one here, it takes from here again to here. I hope this is clear. Minus 1, 0 to 0, 3 pi by 2. This is quadrant 3. Motion from left to bottom. And then we have got the quadrant 4, which is actually again starting from from the bottom to where we started. So it starts from here and goes back to here. Now what I was telling is that here you can see minus 3 pi by 2. This is something strange. I mean to say, we have mentioned this, but we have actually not mentioned what it is. So here I would like to tell you that this is not a coordinate on the curve, right? So minus 3 pi by 2 is actually mentioning to the parameter value t equals to 3 pi by 2. So just remember that this is just the parameter value, so it has nothing to do with actually 3 minus pi by 2. This is not referring to the coordinate, but some of the books they refer this as minus 3 pi by 2. Okay. So from here now you can see that if you are trying to construct an asteroid curve, so what it will happen, that if you take a small circle and you roll inside a big circle 4 times exactly, then what you get is an asteroid curve. So if I magnify this to another animation, you can see how it happens. Now this is typically which is called a hypocycloid. Now I'm not mentioning or telling you or explaining what is hypocycloid. I will do it in another video, but this is an example of hypocycloid. So the question is that why does the asteroid come from this rolling of an inside circle, small circle, and rolling it outside? So if you take a small circle and roll it inside a large circle, that is exactly 4 times bigger. Right? So this is not just a neat coincidence, it is actually a case of family of curves which is hypocycloid. So what happens typically over here, if the ratio is 1:4, the curve traced four cusps, right? So each cusp forms when the point on the rolling circle touches the larger circles at specific intervals. So the resulting shape is closed and symmetric, and it has exactly sharp 4 corners. So that is why the r radius is 4 times the r. That it is making a 4-cusped hypocycloid, or in simple terms it is called an asteroid. So if the ratio is 1:4, the curve will trace 4 cusps. each cusp forms where the point on the circle is rolling and where it touches the larger circle, and the resulting shape is a closed symmetric, and exactly it has got 4 sharp corners, making it a 4 cusp hypocycloid, or in simple terms a cycloid. So as you can see, the red point on the rolling curve traces out the curve. So it forms a cos cube t and y of t equals to a sine cube t, where a would basically mean the value, that is in both cases it is scaled outward and inward depending on the value of a. And if you take a equals to 1, then obviously you get the standard asteroid. So what I am trying to make a point in this video is that this hypocycloid is something which is internally forming by rolling the small circle inside the large circle. Right? So it is a special case of a family which is called hypocycloid. What is important is that the ratio of the radii must be 1:4. So that the cusps are rotated 4 times and it has got 4 sharp corners, and technically it is called a 4 cusped hypocycloid, which in general terms mean what is called an asteroid. So if you take a, that is a value equals to 1, then if you plot that value you get a standard asteroid. So this is how an asteroid is being formed, and the asteroid looks like this with a ratio of 1:4. Now that we have seen the shape and the beauty of this asteroid curve, you can see that from circle we come to asteroid. We have defined the 4 quadrants, right? Now I would like you to imagine that if a point is moving along as the time passes, so what if a particle traces this curve over time? Now we need to know how is it moving, which direction is it heading, and for that we will now move to the next part of our video where this motion will be taken into account. And for that, first we have to understand a basic concept of geometry or differential geometry. It is what is called a vector valued function, coming up in the next part of our video. So what is a vector valued function? In general we will say that this is it takes a number, for example any number, and a time t, and returns a vector pointing to a location in space. So in order to make things clear, let us imagine this is a robot's hand and it points at a certain point. So if you take a time t, for example, and if you program that robot, then you will able to find where the particle it is at the xyz coordinate, considering that we are taking a 3-dimensional coordinate. So it tells you where the finger is positioning at that time, which includes the x, y and z coordinates. Now as you can see, in 2-dimensional a vector valued looks something like this. So what does it mean? It actually means simply it collects the x and y values together into a single vector. So we have mentioned t, which maps a vector in space. R and t are basically what are called the positional vector. This is taking 2 values, x of t and y of t, for a 2-dimensional diagram. Now you note something, there are some angular brackets. It is not the usual braces, these are the angular brackets. What does it mean? So it actually is used to represent a vector in general component form. That means if I take v equals to ab or abc, which is for 3 dimension, and if I put the angular brackets in between, it will be just simply like this: v equals to ai plus bj. That means it is taking the ith component of a, jth component of b and kth component of c. So the angular brackets are nothing, this is just packaging the x and y positions together. It is like saying here is where the particle is at time t, it goes this far in x direction and that far in y direction. Right? So here you can see, if I take the xyz coordinate again, then what we will get is basically a vector which is pointing right from the origin towards that point. So the pair becomes a position vector, an arrow from the origin to that point. So obviously from here we can write the vector valued function which was there in asteroid, cos cube t sine cube t, as this one within the angular braces, and this one if I are taking the component x of t I and y of t j. I have put those hats on it so that it denotes what? It is basically talking of a single vector. That means its value is 1. Okay, so from here, as we have understood the vector valued function, let us see how the vector valued function will first look in a circle. So here is a nice animation. You can see the circle is going around. It will look simply like this. and then we will get this. So at t equals to 0, it will have some value. At t equals to pi by 2, it will have some value. So at each t, the vector points to a position in the circle, and the tip traces as it goes on and on as t increases. What happens for an asteroid? Simple, it will be the same. The position vector will be r of t, and it would be cos cube t and sin cube t. So this is also a vector valued function which maps the value t in this interval for a point and asteroid. So it gives a vector which is from the origin to the point, which I have somehow not drawn over here. So you can just imagine a red line or any line pointing from this value to this. Now, there is something which is very important for a vector valued function that you need to remember. So what you need to remember, that remember a vector valued function actually gives you a single straight arrow. So a vector valued function is not the curve which is tracing around. This is a point of confusion which arises in certain students. I've read in many books, it tends to get confused. So remember, it is not curved, right? It is just a line segment from the origin to the moving point. So at any point, for example, on the left hand side of your screen, as you can see the circle which is animating and going around, so at any point of time, so the time flows and the vector traces out the circle. At any point of time, if I stop, say for example, I stop this curve, right? So what I will get is here, and there will be only a single straight line. So for example, I have stopped this circle at t equals to pi by 4. So what it will give at that specific point, it will show you the arrow, whatever the vector it is, from the origin to that point, drawn as a straight arrow. So the red arrow, as I was telling you, if you stop the movement, then it will be just a red arrow. That is the vector at a particular time t, that time t where you have stopped the animation. So remember, so whether it is a circle or it is an asteroid or any other exotic shape that you're dealing, if you're freezing time, at any instant, the vector valued function gives you a straight vector. So it is not something which is going around at you. As you stop it, it will just be a straight vector. Now, so far we have seen that how the vector valued function tells us where the particle is at each moment. It gives us the position. But motion is, as you understand, is not about position. It is about change. So next comes the big question to understand how the particle is moving, and we'll look at how the position changes with time. In order to do that, we now understand what is a velocity vector. Now you might say that why I have told about the vector valued function first and then coming to the velocity vector, things will become very clear. So when we talk of a velocity vector, it tells how the position is changing with time. So if I take the position of a moving particle at time t, this one, then the velocity vector is just the derivative of the position vector, right? So we start with the position r of t of the position vector, which gives us the location of a particle time, and then we take the derivative and we get the velocity vector. This looks something like this. Don't worry, I will give you a very simple derivation which follows the chain rule of calculus on this part. So from here, what we can understand is that this term Vt is the velocity vector. That means which tells you how fast and in which direction the particle is moving. If you take dr by dt, obviously it is simple, taking the derivative of the vector valued function r of t with respect to time. And if we differentiate the component, that is the x component separately, y component separately, and then take together, we get something like this. So here dx by dt obviously means rate of change of position with respect to time, and dy by dt rate of the change of the y position with respect to time. So all in all, what we can say is that mathematically we just took the derivative of the x part and the y part separately. So this vector Vt points along the curve showing the direction of motion, and its length tells us the speed. Okay. Now coming to the visual, how does a velocity vector looks like? So here you can see, again, these are, this is basically, I have taken the velocity vector of a circle. It would be minus sine t cos t. And if I take the radius as r, so what we get is all this one, v, all these boxes, these are basically the velocity vectors. And obviously you can see from here that the velocity vector is tangent to the circle, showing the direction of motion. Its length obviously, and its, I mean to say, the magnitude is 1, which is making it is a uniform speed around the circle, and this is actually the tangential velocity or the velocity vector which is moving. So what it refers is that each velocity vector is number one tangent to the circle, as you can see in the diagram on the left hand side. It is perpendicular to the radius to that point, and it is pointing in the direction of motion, clockwise or counterclockwise, whatever the way you want to take. So this actually sets thing in motion, right? So we got the velocity vector of a circle. We know it is tangent to the circle, and we have already understood what is a velocity vector. We have seen that it is basically a derivative of the position vector. Now the big question comes, how do the velocity vector looks like in kind of a in an asteroid? Because we are learning the asteroid curve, and it looks like this. All these red arrows, as you can see, these are basically the velocity vectors. So the black curve is the asteroid given by the parametric equation this. The red arrows are basically the velocity vectors. Now remember, the velocity vectors will be moving along the curve, right? So it would be going this way and then coming back, and at the cusp the velocity will be zero. We will come to that point, and then it does so. So this is how more or less the in general the equation looks like. So it tells us both how fast and in which direction the particle is moving. So each red arrow is tangent to the asteroid and shows the direction. So the tip of each arrow, remember the tip of each arrow, red arrow, shows where the curve is heading towards next. So it is going up, then down, then this way, and then this, and then this. I could not show with a pen and a paper, it would have been better. But anyway, these are not from the origin but sit right on the curve, giving the particles instantaneous direction and speed of motion. And in order to get that instantaneous motion, we are doing the derivative. So all flows in a very nice pattern. So it tells us both how fast and in which direction. And this equation captures the unique geometry of the asteroid through sine and cosine function raised to powers, and it gives us this beautiful geometry. And that is why we say that mathematics is indeed beautiful. You can now see that how the beautiful curve and the shape it manifests through some beautiful and simple equations. Okay. So now we come to the next point. How do we get to this equation? I will do some very simple steps. So first of all, in order to get to this equation, we understand what is a parameterization, right? So r of t is given by this xt cos cube t and yt sin cube t. What do I mean by that? This is actually the particle is tracing from 0 to 2 pi. 0 to 2 pi means the entire this one, right? The 360 degrees, right? Now step 2 is that we differentiate the first component cos cube t. We get this value. Then using the chain rule, we get this simple. And then we differentiate the y of t sin cube t, and we get this value, and then the full vector we combine together to get this value. That's it. It's very simple. Just to show you step by step how it actually looks like. So now you can see that I have plotted this value t is equal to pi by 2. These are different coordinates. You have already looked in that. So if you're talking of this particular equation, so the direction is what? Direction is at any moment of t, the velocity vector is tangent to the curve. We will come to this tangent part right now, but just let us understand that it is tangent to the curve. And that means it hugs, right? It embraces the path of that point and shows the exact direction. If we talk of a magnitude, then the length of this vector, how long the arrow is, it tells you the speed at which the particle is moving. We'll come to that speed, magnitude and the speed part later. But what is most important, when you go to the cusps, right, where cos t equals to 0 and sin t equals to 0, it means that the speed vanishes over there. That means what? The velocity, yes, over here, these blue arrows show the cusp. So the velocity vector vanishes, the particle momentarily stops, and there is no direction of motion at that instant. So if the arrow is short, the motion is slow. If it is long, the particle is moving fast. This means that the speed varies along the asteroid, especially near the cusps, where the speed drops to 0, and in the middle parts where of the each lobe where it speeds up. So we talk about direction. The vector is tangent to the asteroid. So we now come to the next part of our video, understanding what is the tangent line. Now I won't take too much time to explain this. We have looked in our school days. So this is what is called tangent to a curve. This is a nice animation which shows how the point and the tangent line is moving, and this is another example of the tangent line. All of this says one single thing: the straight line that just kisses the curve at that point is what is called a tangent line. Now let us look in this part of our page. I draw a curve something like this, right? This is a nice curve. I've taken this blue dot, this is the line, and this line kisses this point, and so it is called a tangent line. Now I am drawing a velocity vector along this one. The red one is basically what is called is the velocity vector. So now first we will take what is called the position vector, RT, right? So position vector of a particle on a curve at a time t, it gives you the actual point on that curve. So it is basically RT equal to cos t sin t. Next we take a velocity vector. Velocity vector is what? If you take the derivative, it will be dr by dt. So the direction the particle is moving at time t, the rate of change of its position, and it is the direction of the tangent line. So the velocity vector, remember, I have drawn it over the tangent line. It can be anywhere, but it should be along the curve, right? And in order to calculate tangent line, we do this calculation. Ls equals to RT plus S times V of t for all the scalars S which are a family of R. That means the real number. Simple. Now you might be wondering that what this S is about. Remember, this S is nothing. It is just a scalar parameter. Right? It is just a scalar parameter. That means it lets you know how you move forward or backward along the tangent line. So if I take, say for example, if the scalar is S equals to 0, then I'm standing on that point. If S is less than 0, I'm moving on the opposite direction. Right? In the opposite direction, if S is greater than 0, you're moving in the direction of the velocity vector. That is Vt. So together we write that we start at the point r of t, and then we move in the direction of the velocity vector, either upward if it is greater than, downwards is less than or equal to 0 at that point, and simply we are taking the steps that we are taking, how many steps of S, that is what it is, and together this is what this full equation is. So it tells that it traces out the full tangent line at that point on the curve. So this is what it is. So to turn the page, let us understand this a little bit more clearly. So you are holding that arrow, that red arrow, right? This is the velocity vector, and it is showing the direction in which the particle is moving. The tangent line is what? It is the infinite extension of that arrow, a straight path going along through the red dot in the direction of the motion. It won't be red dot, it will be blue dot, I'm so sorry. And by scaling Vt, you generate new points on the tangent line. So the tangent line is the infinite extension of the arrow, a straight path going through the blue dot in the direction of motion. So for example, if the blue dot is a red car, for example, then the velocity vector is the short arrow showing the direction and speed of the motion, and the tangent line is like the road of the car, and it would keep following and following, moving in a straight line from that instant. So this is what the tangent line's important is, and how tangent line and velocity vector are related. Now if I take a sample, for example a circle, and if I take the tangent line as this point, so the tangent line would be this, doing the calculation, and which will give us this value, and this actually means that the line passes through the point RT, the position vector, and it extends in the tangent direction. Now here is another important thing which you might have missed. There is a dot, S dot Vt. Now what is this dot all about? Is it a dot product? The answer is no. This is a scalar multiplication. Remember, it is not absolutely a dot product. So what do I mean by that? So for example, if I take Vt as a vector in say R2 or R3, whatever, you can think of n dimension, then S is just a scalar number, right? A real number, 2, 3, 4, anything. And S dot Vt, which is a scalar multiplication, only scales the vector. That means it makes it long if S is greater than 1, it is short if S is less than 1, and it flips the direction if S is less than 0. So this is, remember, it is nothing related to a dot product. Although it looks like a dot, it is a scalar multiplication. So it is just stretching or shrinking the operation. It is not a projection like the dot product. It is only what is called a scalar multiplication. It is scaling that value, nothing else. Okay, so how does a tangent line from the circle it looks like on an asteroid? Now this is how it looks like. I'm thankful that ChatGPT has drawn this wonderful diagram. So this one, as you can see, first of all, the point is t equals to pi upon 4, whatever be the value. This is the blue dot. The velocity vector at that point is this thick blue arrow, the tangent line. Sorry, first the tangent line. It is the red dashed line, which is the line passing through the point in the direction of the velocity vector. This blue one, the thick one, this is the velocity vector, which is showing along the direction. And the tangent line, as you can see, aligns the vector at that point. It represents the instantaneous direction of motion. So the main takeaway from this part of our video is that the tangent line aligns with the velocity vector at that point. It represents the instantaneous direction of motion, and the motion is not a cusp. So the velocity vector is non-zero and it is well defined. Now, if you see that when I take the velocity vector, so this is where the point is 0, t equals to 0. So the plot here shows the situation at the cusp of asteroid when t equals to 0. And the point on the curve is at 1, 0. So the velocity vector is 0, right? No arrow is visible. It means the particle is at halt. The tangent line is degenerated. Degenerated means obviously it's just a dot. I cannot put up a tangent line over here. It is undefined because the particle has come to a halt. So there are few things which are happening over here. Number one is that the curve is, remember, still continuous, but it has a corner, not a smooth kind of a surface. And so no unique tangent line exists. That is why the velocity vector vanishes over here. So the tangent here, as you can see, the value is 0. So there is no unique line, which is why the velocity vector also vanishes. So this confirms our statement that no motion means no direction, means no tangent line. So this is how the asteroid or the velocity vector and the tangent line over it comes into play, comes into shape. So when it is just a point, curve is continuous, it has no corner, the velocity vector is 0, so the value of vt is 0, and there is no unique tangent. Now you might have a doubt now in your mind that this velocity, speed, etc., that we are speaking in terms of differential geometry, how is it related to physics? Because these are terms are related to physics, and in Newtonian mechanics we do carry and we do calculate. In order to tell that, first of all, look in this curve. Now you already understood this is what is called the famous Newton and Bernoulli's brachistochrone problem. But I am not going to explain the brachistochrone or the cycloid problem over here. But what I want you to look is that you can see these particles. You first see this one reaches the 2, and then the 3, then the 4, the 5, and then the 6. The black one reaches at the last. So as you can see, the orange one drops right down. As you can see, here it comes. Here it first touches, then the second, then the third, then the fourth, the green one, then the blue, then the purple, and the black one touches at the end. So the question is that now that we know velocity vector gives us both direction and rate of change of position, the natural question is coming is that how fast is the particle moving? That means what is the speed? Also, is this speed something related to the speed in physics? How do we determine this speed? Now, in order to do that, you have to wait till the next video. So we put an end to today's video by explaining tangent line, velocity vector, and also the vector valued function. So thank you very much for those who have taken time to watch this video. If you have liked, please do subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. You can also subscribe to my other channel, and you can write to me for any other queries which I try to promptly answer. Physics for Students will be soon back with more videos and completing this series on differential geometry. We'll see you soon, but till then, may the good Lord be with you.